Hello and welcome. I hope you can all hear me. Welcome to the walkthrough of the OCR Depth in Physics practice question paper. This is the practice paper, not the specimen paper. I've already made videos for the specimen paper. You should be able to find those on my channel. Please subscribe if you're interested. Where I can hear my own voice in my head. Let me close the window that's doing that. That's it. Okay, sorry. Yes, this is the Depth in Physics practice paper. This was an absolute killer paper. It's hopefully the real thing won't be quite as bad. The mark scheme in particular is really quite strict, but even so, I'll go through all of the questions I've spent today, making sure I understand every bit of the mark scheme so I can explain it to you. And also attempted this paper for real. I didn't do very well myself, so rest assured, you're not the only one who struggled with this particular paper. So let's make a start. And the first question is a relatively straightforward question. Define the moment of a force about a point. Well, that's one of the definitions you sort of need to memorize. You can use the tool Memorize or Quizlet or anything like that to try and memorize these things. Also, if you go on my website, cowenphysics.com, you'll see I've put a list of definitions up there. This is one of them. So the definition of the moment of a force about a point is the force times the perpendicular distance from the pivot. It is absolutely critical that you say perpendicular, and it's absolutely critical that you say from the pivot. The second question actually is something that students often get confused between these two, between stating the principle of moments. But this is again something that you just need to memorize and get it absolutely nailed every time you're required to recall it. So the principle of moments is that the sum of clockwise moments around a point is equal to the sum of anti-clockwise moments around the same point. Doesn't perfectly match what the actual mark scheme for this paper says, but what I've written here is it would certainly get you the marks, I'm sure, and it's also what mark schemes going back years for OCR have kind of identified as the best definition of the principle of moments. So I'd stick with that. The sum, very important. You say the sum of or the total, and it's usually quite important as well that you say around a point. So that's the kind of the definitive definition, if you like. Part B gives us a question about a crane here. It's saying the crane arm can pivot around point A, and it's supported by this cable along here, BC, as shown. It says the arm is in equilibrium. Draw and label 3 arrows on figure 1 to represent the 3 forces acting on the arm. So the first weight should be the most obvious one here. The center of mass of the arm is at D, so that's the point from which we need to draw an arrow vertically downwards. I've not drawn that quite in the right spot there, but thereabouts it should be vertically downwards, and we need to label that the weight. The second most obvious force should be in this cable, BC here. That will be acting from right to left along the cable. I'm not worrying too much about the size of these forces. We don't know the relative size of them. Again, I'm not very well drawn that. Let me try that again. It should be going along the wire. Third time lucky. There we go. Okay, and the third force acting on the diagram. This is what's going to bring the whole thing into equilibrium, is acting down at point A. It's the contact force between the beam and point A. Now, the direction of that, you might assume it would be along the beam from A to C, but that's not the case. It's actually a dashed line continuing up from here, from the weight up to the tension, and it will be acting up there. That would make sense if we take these arrows off and we sketch a triangle of forces. You'd see that the line would have to go up at such an angle, that point there. So it would go through that. I'm not going to draw it all the way up like that, but that's our angle there. Don't forget we need to label our forces. So this one is the tension, and this one is a contact force. So there were 3 marks available for that question. I think to get all 3 marks, you needed to have labelled all 3 forces. Let me just double check that. Yes. And part 2 says calculate the tension in the cable BC. Now, there's an alternative method to doing this, which stumbles upon a similar answer, but it's not a correct method, and it wouldn't work in a different question. This is a moments question. That should be really obvious from the first part of the question, which was asking you about definitions of the principle of moments. So we need to take moments around a point in order to solve this. Now, we're going to take moments around point A. And what's made tricky here is that definition of the principle of the definition of a moment is the perpendicular distance from the force to the line of action of the force. So we're interested in parts of the diagram out over here. So let's say that's our line there from A to D, and we have our weight acting down there. The perpendicular distance is along this side here. So we know that that angle is 30 degrees. So and we know that this length here is 3 meters. So we'd have to use trigonometry to work that out. So you could solve that using SOHCAHTOA. We know we're trying to find this distance x here. We know the hypotenuse, we know the adjacent. So we can use the cosine, and what that will give us is that x equals 3 cos 30, which is 2.6 meters. So that tells us that the perpendicular distance between A, where we're taking the moment, and the weight is 2.6 meters. The only other force that counts here, because the contact force acts at A, so there's no distance, so it doesn't provide a moment. The only other force we're interested in is the tension, and again, we're interested in the perpendicular. I drew that on the diagram here. Is this distance here? So once again, we can sketch a triangle. We know that that angle there is 60 degrees. Of our right angle at A. We know that the total length of the beam, so that's A there, and that's the total length of that beam is 3 plus 3, so that's 6 meters. And we're interested in this distance here to Y, that is T running along there. So we can use the cosine again. We know the adjacent and the hypotenuse, and that will give us that Y equals cos 30, which is actually 3 meters. So we now know that the perpendicular distance to the weight is 2.6 meters, and the perpendicular distance to the tension is 3 meters. There are alternative ways of approaching this. That's just one way. So now we can say that forces are equal to the clockwise moments are equal to the anti-clockwise moments. So we can start with the weight, which is providing a clockwise turning effect around A. So the weight is 1800 multiplied by 9.81. We multiply that by the perpendicular distance, which we've worked out to be 2.6. And that is equal to the anti-clockwise moment. So the force causing an anti-clockwise moment is the tension, which is what we're trying to calculate. That's T, multiplied by the perpendicular distance to that force, which is 3 meters. This, plug in our values, and that would give us an answer of T being 15 kilonewtons, or 15,300 newtons, and that is the correct answer. Now, this question had me thinking for quite a while this afternoon, and it's certainly not one I got right when I tried this myself a few months ago. The arm is rotated about A by shortening the cable BC. If we can just scroll up so I can show you the question again. So the arm is being rotated. So A, the beam A, D, and C, that's going to kind of rotate anti-clockwise around A. The rope at BC is getting shorter, and it's no longer horizontal. So the whole system is changing in quite a complex way. There's 3 marks here for explaining whether the tension in the cable has increased or decreased. I'm going to begin by just sort of sketching it out. First of all, drawing B, there's C. We know that we've got the tension T acting along there. That's moved up like that. It's no longer horizontal. We have our beam there down to A, and that is now at an angle here. And we know that theta now is greater than 30 degrees because that angle has increased. BC has got shorter. If that angle there has increased, it makes sense that this distance here has got bigger. And the way to be sure about that, imagine if the whole thing went the other way. If this angle got smaller, eventually the whole thing would concertina together, and D would get smaller as well. So in this case, D is increasing. So the perpendicular distance, that's this distance I've just labelled with a little d here. Sorry, no, it's not. That's not what I'm talking about. Sorry, the perpendicular distance to along here. I've forgotten to do that. We've got our weight acting down. So the perpendicular distance, SW, sorry. Perpendicular distance here between A and D has got smaller. You imagine that would keep happening if the beam AC keeps rotating in the way it is. Eventually it will become vertical and the perpendicular distance would become 0. So the perpendicular distance to the weight is decreased. Therefore, we have a smaller clockwise moment because the moment is the force times the perpendicular distance. The perpendicular distance has decreased, but the force has stayed the same. So overall, we have a smaller clockwise moment. So that's the answer. So let's start writing this up here. Clockwise moment caused by the arm weight has reduced. The other thing that's happened is this distance I've labelled little d has decreased. That means that the where are we? Sorry, that means that the moment produced will be smaller from the tension as well. So we can say that the perpendicular distance from A to the tension, that's along the line BC, has reduced. Therefore, the tension must be smaller to provide moment. a pretty complex question to get your head around, but there are 3 marks available if you do crack it. By the way, throughout this, if you want to ask any questions in the chat box, that's a good idea. I'll try and look occasionally, but it will take a while to get through this paper anyway. So I think what's probably best is if you save questions for the end, then I'll take questions for maybe 10 minutes or so at the end of the paper. Okay, question 2. We have an experiment. This is one of the standard experiments you should be aware of. There are slightly different alternatives to how to actually carry out the experiment in terms of it may not be an electromagnet at the top. It could just be a kind of a physical spring or something to release it. But the way it works is always essentially the same. You have something that starts a timer when the ball is released and a trapdoor at the bottom, some sort of switch at the bottom that will stop the timer when it lands. So this is an automatic way of measuring the time that a ball is dropping for. And the idea is that you use the results combined with the distance to determine G. Now, the first part of this question should cause you no problems at all. However, I am aware some students were a little bit confused with the terminology, and this is important. This is something that you should be aware of as one of the practical skills, is this terminology at the top of our columns here. The idea of separating the S and the M by a slash. What that means is the S is displacement measured in meters. This is time measured in seconds. This is time squared measured in. I know that some students interpreted this as being T divided by S, thinking the S was the distance over here, and that caused an awful lot of confusion. So you will always see a slash. I don't know why they use a slash and not brackets, but they use a slash to separate the quantity from the unit. So just be aware of that. Other than that, this should be a very straightforward question. You're just filling in these 2 remaining points here. So 0.47 squared is 0.22, and 0.51 squared is 0.56. You then need to plot those points on the graph and draw a line of best fit. So I'm going to try my best to plot these accurately, but it's pretty difficult on a graphics tablet. So the first point here we have at 0.22, which is going to be around here, and crossing the line 0. Forgive my dodgy plotting. I wouldn't get any marks for the quality of my plotting. You would need to be very neat. The guidelines usually say you need to be within half a small square of the correct position. So do spend time checking. You will almost certainly, I'd say, be asked to plot something in a graph in this paper, because they didn't ask you to do anything like that in the breadth paper, as far as I can remember. And at 0.2, what was it, 0.26 and 1.2, so that's up here. Want you to draw a line of best fit. So you'll see most of these points are all in a neat line anyway. We can draw a line of best fit like that. Again, there's no need for you to continue it beyond the edge like I've done. I'm just not very neat at drawing on this tablet. The next step, it says determine the gradient of the line. Show clearly you're working. It's very important you show you're working here. And the official guidance for how you should determine the gradient of a line is that you should draw a triangle on the graph, and that triangle should represent the hypotenuse of that triangle should be more than half the length of the line of best fit itself. So I'm going to draw my triangle here. You could draw it even bigger if you wanted to. So across at 0.2, and I'm going to draw down at 0.3, like so. And then you need to take read-offs from that. We know that the gradient of a line that we should know is delta y, the change in the y, divided by change in x, or in this case, change in s over tangent t squared. So our biggest y value is 1.4 from our triangle. Our smallest is 0.2, and doing the same in the x direction, of 0.3 minus 0.06. And you don't have to have chosen these exact points on the graph, but your triangle must be more than half the length of the line. And if you plug these numbers into your calculator, you'd find that gives us a gradient of 5.0. There would be a small amount of tolerance in the mark scheme for this kind of answer, but not a great deal, especially given all of these points do lie very, very neatly on the line of best fit. Now, that's the easy part of this question. The analysis part of it is much trickier, but if just bear with me, I'll do my best to explain where the marks come from here. So the student expected the line to go through the origin and have a gradient of g over 2. Well, if you look, actually 5 is not bad for g over 2. That would suggest a g of 10, which is not far off 9.81. The device he used measured to within 0.01 seconds, and the distance s was measured to within 0.01 meters. So the fact that the line of best fit does not pass through the origin is unlikely to have been caused by random errors in his measurement. Justify this statement. Well, the first thing to note when we look at our graph here is that all of the points are below. I'm going to use, if I can see, how do I change color? Not sure. And it does go through the origin. You'd see it would go up like that. Okay, so what we have here is the expected line of best fit, and we can see that all of our points are below that. It's not a random scatter around that. Every single point is the same amount below the line. That suggests a systematic error rather than a random error. So that's our first bit of reasoning we can say there. So all of our points are lower than the theoretical line of best fit, distributed randomly around it. But there's another reason as well, and this it took me a while to understand what the mark scheme said when I was reading this earlier. We know that the timing device was to within 0.01 seconds, and the distance was to within 0.01 meters. The mark scheme refers to range bars, and that's a little bit confusing because there are no range bars in the graph. But you can add range bars because you know the uncertainties in the measurements. If every distance was actually potentially, because it was only measured to the nearest 0.01 meters, every distance could potentially be 0.01 higher. Now that is only half a little square here. So you could, on every one of these points, range bar half a square above. I've done that pretty poorly there because it's quite difficult to be very precise here. I can do that here as well. And you can see that those range bars, at least for the distance, do not make a difference. Not enough to justify why the line is up. Something else has happened that has caused it. It's not just an inaccuracy in the measurement of the distance. You can do a similar exercise with the time. It's a little bit more complicated with the time because obviously that is applied to the values and then squared. So, for example, if every time was, shall we say, if every time was slightly lower, because that's what would bring the line to the left, if every time was slightly lower, the maximum lower it could be with that uncertainty is 30. So on, you can fill in all of these down to, at the bottom here, 0.55 would become 0.54. You would then square each of these. So 0.5 so 0.54 squared is 0.2 0.292. So that's the smallest possible value of t squared based just purely on that uncertainty in the measurement. You can see that that barely changes it as well, 0.292. That would still around here. So a slightly bigger effect than the distance, and that's the largest effect because that's the largest number, so that you've got the biggest effect from squaring it. The range bar will be shorter if we're working down at the other end of the graph. And you can see that is still not enough to cause that offset. See what I mean about this being a slightly complicated and involved answer here? So what we can add to this is we can say that the error on each point from measurement uncertainty is not enough to move the line of best fit through the origin. Okay, and the second part, explain how a systematic error in each of the measured quantities could contribute to the line not passing through the origin, and what effect, if any, each would have on the gradient of the line. So if we can see that we're looking at the graph, we can see that all of the s's, all of the distances are too small. The distances should all be a little bit higher, and that would move our line of best fit up to where the green line is there, the theoretical line. So we can say that s is too small. So a larger s shift the whole line up. Now that will not affect the gradient because every value on that line is just going to move up by the same amount. That is not affected. However, it's slightly different for time. We know that the time is actually a little bit too. The time is a little bit too large, and that a smaller time would be needed to move the graph to the left. But the effect of a smaller time would how do I phrase this? So because time is being squared, the larger the values of time, the more the effect of squaring it will be. So you don't get an even effect. You can try it if you want. If you went through that results table and change them all by the same amount and squared them all, you'd see that the larger numbers would have a bigger effect on them than the smaller numbers. Due to t being squared, the error increases for higher values of t. Therefore, gradient becomes more steep. That would affect the gradient. So an error in S doesn't affect the gradient, an error in T does. The rule of thumb for you to remember in the exam for that, question for them to ask, is that if you're not squaring it, if you're not doing anything to that to every number, then other than just adding a value, and an uncertainty will not change the gradient. But if the value is being squared, then an uncertainty will change the gradient. So suggest one possible source of systematic error. This needs to be consistent with what we just said above here. So we either need to do something that would explain the S being too small, I don't know, maybe a parallax error on the ruler perhaps, I don't know, or that explains T being too large. I'm going to go with T being too large because there's a nice answer here, which is that the time the trapdoor to close fully and close the switch. So that would be a source of systematic error, as in there's a hits the trapdoor it takes time for that trapdoor to close and therefore close the switch. So that time has not been accounted for. Perhaps that is the source of our error. That's certainly an acceptable suggestion. Okay, let's keep moving on to question 3. Question 3 is a question of two halves. It begins with some mechanics and ends with some electricity. So we have a swimmer. They give the mass and the weight of the swimmer being lifted vertically upwards from the sea. And the cable is massless. And it tells us that for the first 1.5 seconds, the tension in the cable is 670 newtons. And from 1.5 seconds onwards, the tension reduces to 640 newtons and stays constant. So we need to use Newton's laws to describe qualitatively the motion of the swimmer for the first 4 seconds of her ascent. So from t is 0 to t is 1.5, we know that the tension acting upwards is greater than the weight. So there is a net force. And therefore a there's a net force and therefore a constant acceleration. For t, when it's between 1.5 and 4 seconds, so that's the rest of the journey, we know that the tension and the weight are both 640 newtons. So the tension is equal to the weight. So there is no net force. Therefore, there is zero acceleration, which means we have a constant velocity. That's actually enough, or just saying the constant acceleration, constant velocity actually here are enough to get you the marks. Although you should note the question says you use Newton's laws to describe it, so we can relate these to Newton's laws. Force being proportional to acceleration, well, that is Newton's second law. And the idea that an object moves at a constant velocity unless there's a force acting on it, well, that's an example of Newton's first. You could include those details as well. Now, the second part of this is a SUVAT problem. We need to show that at 4 seconds, her height above the water is more than 2 meters, and she's rising at about 0.7 meters per second. So remember, there are 2 stages of the journey. There's a section where she's accelerating and a section where she's traveling at a constant velocity. If we can find the velocity at the end of that first section, that gives us at the end of the journey as well, because once you stopped accelerating, that velocity stays constant. So that's our first job, really, is to find that. Well, actually, our first job is to find out what the acceleration is, because we don't know. We need to use F equals ma. We know that you've got to remember the very important F in this. F in F equals ma is always the net force. So we have our acceleration is equal to the net force F divided by the mass m, which gives us 670, 640, and the mass 65, which gives us an acceleration of 0.462 meters per second squared. The next stage here is to consider the first 1.5 seconds. So as with all SUVAT problems, really good write out SUVAT. So S, well, we need to find that out because we need to find out the total distance lifted. So S will get us part of the way there. U, we know to be 0. V, we also want to find out. That's the final velocity. Normally in a SUVAT problem, you've got one thing you don't care about, but in this one, we're going to need to do SUVAT twice because we've got 2 things we don't care about. It's no big worry. A is 0.462. We've just worked that out, and T, we're only interested in the first 1.5 seconds. So t is 1.5. So let's begin by trying to work out our velocity. So we know v, u, a, and t. So the obvious equation to use is v equals u plus at. The initial velocity is 0. She's starting from rest. So plus 0.462 times 1.5, and that gives us 0.692 meters per second. Now remember, once you stopped accelerating, that velocity stays constant, so that speed is going to be our and also remember, it's a show that question. It says that the answer is expected to be about 0.7 meters per second, and that's precisely what we've got, 0.692. Next step is to do SUVAT again to find the height that the swimmer rose through during just that first 1.5 seconds. To do that, we can use S equals UT AT squared. You can use an equation that would include S and V, but it's best not to, just in case we made a mistake with V. We know that we're looking for S. We know U is 0. We know A, and we know we are confident about T as well. It's 1.5. So again, half times 0.462 times 1.5 squared, and that gives us a distance traveled. This is just, remember, just during the first part of the journey of 0.520 meters. Not very far, but half a meter. And then remaining part of the journey, 1.5 seconds to 4 seconds. She's traveling at a constant velocity, so we can use speed as distance over time. You don't need to use SUVAT because acceleration is 0. So that gives us a displacement S equals VT, which is going to be 0.692 multiplied by 2.5, which is the time from 1.5 to 4 seconds. And that gives us an answer of 1.73 meters. And you need to add that distance to that distance, and that will give us an answer of 2.25 meters. And again, that fits in with what the question said, that it's more than 2 meters. Now, part B stays with the same theme of this motor, but it's now a question about electricity. And it says the cable is attached to a winch rotated by an electric motor in a rescue helicopter. The height of the motor has an EMF of 28 volts. The circuit has a total resistance of 0.11 ohms. When the swimmer is rising at 0.7 meters per second, the motor draws a current of 30 amps from the supply. So under these conditions, calculate the power lost in the electrical circuit and the efficiency of the motor. So what it's worth understanding what it means by the circuit here. It's referring to the wires and so on, all the circuitry connecting the motor. So it's not counting the motor itself when it says that the circuit has a total resistance of 0.11. It might be easier if I circuit diagram to represent this. We've got our power supply there. I'm going to draw a resistor. This represents the circuit resistance of 0.11. I'm just going to draw a little motor down here to represent our winch motor. And that's our complete circuit. We know that the voltage is 28 volts. We've got a current I here, which is 30 amps. And we know the resistance in the circuit is 0.11 ohms. Now, to work out the power lost, you will almost always, for power loss, use the equation P equals I squared R, and that's no exception. This question is no exception. However, you've got 3 equations on your formula sheet for power. You've got P equals V squared over R, P equals IV. The reason you can't use either of the equations that involve V is because we can't use 28 volts as the V. The V that we're interested in here is the V drops across, the potential difference across just the 0.11 ohms. We don't know that detail. We only know that full voltage being supplied to both that and the motor. So that's why you can't use an equation that involves V, and that's why in almost all power lost calculations you will use I and R. We know I is 30 amps right the way around the circuit. We know R is 0.11. So we can do 30 squared times 0.11, and that will give us a power loss of 9 watts. Part 2 wants us to find the efficiency of the motor. So remember, for efficiency, you calculate that by doing output divided by input. And if you want a percentage, you times it by 100. So the output here, what you're getting out of the motor, is mechanical power. And mechanical power can be calculated using the equation. It's on your formula sheet. P equals the force velocity, P equals FV, which gives us 640 multiplied by 0.7, which is 448. So that is the output power reaching, actually that's lifting the swimmer out of the water. The input power to the whole circuit can be calculated using P equals IV. We know that I is 30 amps and V is 28 volts. That gives us a value of 840 watts. Now, a common mistake to make here would be to go, right, we've got input, we've got output, let's work out the efficiency. That's not quite true. That would give you the efficiency of the whole circuit. We're only interested in the efficiency of the motor, so we need to discount the power that's being lost 9 watts we worked out earlier. So the real input to the motor is going to be 840 minus 99, which is 741 watts. So our efficiency will be the output 448 divided by the input to the motor 741. You can multiply it by 100 to turn it into a percentage. It doesn't matter too much here whether you present it as a percentage or a fraction or a decimal, sorry. And that gives you a percentage efficiency of 60. On to question 4. We have the IV characteristic of a diode. And we have a graph with 3 distinct regions from 0.6 to 0.65, from 0.65 up to 0.75, and then from 0.75 onwards. So we need to state and justify how the resistance of the diode increases, remains the same, or decreases in each section. So let's begin. I'm just going to label these A, B, and C for ease here. I'm not sure I'd recommend doing that in the exam. I'm just doing that to save a little bit of time as I write this. So in section A, well, in all sections, we know that R, the resistance, is equal to the voltage divided by the current. It's really worth stressing at this point, resistance is nothing to do with the gradient on a diode. And the reason for that is because on an IV graph for a fixed resistor like this, where you have a straight line going through the origin, the gradient is 1 over. However, that's only true because you have a straight line going through the origin. At no point in our diode graph do we have a straight line that goes to the origin. We have a straight line towards the end, but it does not continue through the origin, and therefore V and I are not directly proportional at any stage. That's a really important point. So we cannot use that rule there. If you start talking about a gradient, you go off on a very wrong track. So you know that R equals V divided by I, and actually in the first section here, I equals 0. So therefore we can say that the resistance R is infinite. Okay, it's incredibly high. In section B, we are going from a position where we've got an infinite resistance to a position where we have some resistance. Okay, so the R is decreasing. It's the only thing it can do. Once you're at infinity, there's only one way down, and that's to decrease. So resistance is decreasing, and to get the marks here, we should probably calculate what it's decreasing to. So again, we're not doing anything with the gradient. We're taking points from the graph, 0.75 point here, which is 0.75 divided by 20. Let's check the units out, times 10 to the minus 3 ohms. And that gives us a resistance of 37.5 ohms at 0.75 volts. And in region C, we've got a resistance that is again decreasing. It may not be as obvious because you've got this straight line. So many people would look at that straight line and go, you've got a constant resistance. But as I said before, because it's not going through the origin, you do not have direct proportionality. And the best way of confirming that is to take another point along the graph and confirming it that way. So resistance is decreasing. If we take a look at the point here at 0.8, we get a resistance of 0.8 divided by 75 times 10 to the minus 3, which gives us a resistance of 10.7 ohms at. So the resistance again is decreasing to 10.7 ohms at 0.8 volts. And part B gives us our first 6-mark question. This is a new thing for this spec. In each 6-mark question, in each exam paper, you'll be faced with 2 6-mark questions, each of them marked in a similar way to the old GCSE. It's not just as simple as you say something, you get a mark. It's marked according to levels. This question in particular is quite a tricky question, and again, I'll take some time to explain why the answer is as it is. So we've got the circuit here that's being used to produce an IV characteristic for an LED. The student adds an LED with a resistor in series and some meters, an ammeter, and voltmeter, and so on, to take the measurements. So the first thing you've got to do here is to complete the circuit on the correct circuit. So do you choose circuit X or circuit Y? And then you need to explain why you've chosen that one and why there was in there at all. Now, I must admit, at first glance, I made the wrong choice with this one as well. Let me show you why it is not circuit X. So circuit X, if you connected your resistor in, sorry, I've not drawn that very well. If you connected your resistor in, you would have a 100 ohm resistor there, and you'd have your variable resistor there. So what you have is a potential divider. Now, if you've got 2 extreme situations here. The potential divider, let's say you turn it right off so that it has a resistance of 0. Sorry, your variable resistor, let's say you turn it right off so it's got a resistance of 0. That would give you the maximum voltage across the resistor and therefore also the LED. Let's just forget it. Imagine the LED is part of the resistor here for a moment. So we'll neglect the LED's own resistance. So the maximum voltage would occur when the variable resistor is set to 0 ohms. So that means that your potential divider circuit would have you saying that 100 divided by 100 multiplied by V in, which is 6 volts. And that obviously gives you 6 volts. So the maximum voltage you can get from this arrangement is 6 volts. So that's fine. That's exactly what we want. However, the minimum voltage must come when you turn the potential divider in completely the other way. This is a 10 ohm potential divider. Sorry, 10 ohm variable resistor. So if you turn the variable resistor all the way up to 10 ohms, you now have a potential divider. Part we're interested in, the 100 ohm resistor, is divided by the total resistance, which is now 110 ohms, because you've got 10 ohms of the variable resistor and 100 ohms of your fixed resistor. Again, multiply by 6, and you'll see that that gives you a minimum voltage of just 5.4 volts. Bad thing. Okay, all that you can do with that is vary the resistance across our LED and resistor. All we can do is vary the voltage between 5.4 and 6 volts. That's not what we want. We want one that would allow us to vary a much bigger range. So that is no good. That's why we can't accept circuit X, sorry. Circuit Y, on the other hand, if I sketch it out, I'm going to sketch out the two extremes of this circuit. So let's say this is the first extreme. This is our 10 ohm resistor, and you slide A all the way up here, connect your resistor across there. Again, we're just going to forget about the LED for a second. That means that they're fully in parallel with each other, and the 100 ohm resistor across it. So that's our max. The minimum case comes if you then connect it up like this. We have our 10 ohm resistor there. And this time you connect your resistor down here. There is no potential difference across that. All of the potential difference with anything, there's no current going to go through that. It's all going to go through the 10 ohm loop. So the voltage across the parallel branch there is 0 volts. So therefore this is a much better circuit. So the first step we need to do is to draw the circuit, and we need to use the right equipment as well. So we need to put an ammeter in there, and then our LED. It doesn't matter which order we draw these actually. And oops, forgotten the resistor as well. So we have our resistor there, 100 ohm resistor. We need a voltmeter across the LED as well. It's pretty difficult to draw this in the space that they've provided. So be neater than I've been. You've got an ammeter, a series, of voltmeter in parallel across the LED only, and we've got our 100 ohm resistor there as well. Finally, and this is all worth 6 marks, remember, finally, let's explain why that works. So in circuit X, voltage can only vary between 4 volts and 6 volts, whereas in Y, it vary between 0 volts and 6 volts. So that's why we've chosen circuit Y. And the final point of the question, it says, explain why one of the circuits is suitable to carry out the task. Well, we've done that, and we've shown our working as well regarding the potential divider equation. But why is the 100 ohm resistor there in the first place? Well, the job of the resistor is to limit the current in order to protect the LED from damage. That was a pretty tricky 6 mark question, mainly just for trying to understand how these two circuits work. On to question 5. We're getting towards the the end of the exam paper now. Don't forget there will be a bit of time at the end to take some questions. On to question 5, we have a young double slit experiment. The question should be relatively straightforward. You're needing to calculate the wavelength of the light. So we know that lambda equals AX divided by T. Now A and X, I can never remember which way around they are. They represent, one of them represents the slit separation here, and the other represents the separation between the fringes. Now the most common mistake here is to not recognize that actually you've got 5 gaps here. Okay, 1, 2, 3, 4, 5, which means that the separation is actually 6 millimeters, 6 times 10 to the minus 3, divided by 5, which gives us 1.2 times 10 to the minus 3. So we can use that in our calculation. So we multiply together the slit separation and the fringe separation. And we divide that by the distance to the screen, is 1.6 meters. All the way through this, we need to be very careful with units. And that gives us an answer of 6 times 10 to the minus 7 meters. It wants our answer in nanometers. Don't throw away a silly mark by not converting it. So 6 times 10 to the minus 7 by 10 to the minus 9. I'll convert this to nanometers. That gives us 600 nanometers. Part B is our second 6-mark question. This one, you understand what the question is really asking you is not quite as difficult a question as the previous one, but having said that, it's not all that easy to understand exactly what it's asking. You've got a microscope slide, it's been painted black, and 2 slits have been scratched through it to form the double slit. The question says, describe how you could reduce the uncertainty in calculating the value of the wavelength of the light used when carrying out the experiment in part A. So in your answer include how to achieve the conditions necessary to produce a visible interference pattern, and how you would to calculate the wavelength, identifying the measurement which will give you the greatest uncertainties. So make sure you do all the things that it says in your answer section. So first of all, it says include how to achieve the conditions necessary. So let's begin by saying the conditions would be, you need, this is for any double slit experiment, you need light or waves that are from, they must be coherent. They must be from coherent sources. That means they have a constant phase difference. The light coming from the slits must be coherent. So you either use a laser to provide that coherent light, or monochromatic light of one color, perhaps passed through a filter, light diffracted first through a single slit. Now, so that's the conditions necessary, so we can tick that. How would we make the measurements, and which measurement will give the greatest uncertainty? So to take the measurements, we've got 3 things to measure. S1, S2, that is the gap between the slits. That's going to be measured. The mark scheme suggests you could use calipers or a micrometer here. I'm not quite sure how you'd use either to measure those slits on the screen. A better alternative is probably something called a traveling microscope, which is what you'd expect it is. It's a small microscope that can be used to take small measurements this, but by all means, yeah, you could use a vernier caliper instead if you could precisely enough. Now, we know from the previous question that the measurement of S1 to S2 is 0.8 millimeters, and the uncertainty, and this is just something you should be aware of, the uncertainty in a caliper or in a traveling microscope or in a micrometer to the 10th of a millimeter. So that's plus or minus 0.1 millimeters. And now you can use, you can calculate the percentage uncertainty. So that would be 0.1 divided by 0.8 times 100 gives you an uncertainty of 12.5%. Let's take a look at how to measure AB. So that's the distance across the screen. Use a ruler. It's probably the easiest way of doing that. You could, again, potentially use a caliper, but I'm going to go with ruler. So 6 millimeters plus or minus, in this case, 1 millimeter, because that's the precision of a millimeter ruler. And that would give you a percentage uncertainty of 17%, which is quite high. It seems logical that the final measurement D is going to be much less than that, but let's calculate what it is. So D, use a millimeter ruler. So we should say for AB that was a millimeter ruler as well. This time you've got 1.6 meters. Note that I'm doing this in meters now, plus or minus 1 millimeter, which is 0.001 meters. And that gives you a percentage uncertainty of just 0.063%. So really not a lot to worry about there. So uncertainty, well, our greatest uncertainty comes from the measurement of AB. And finally, part C, to reduce the uncertainty in the calculated value of the wavelength, one student suggests making a different slide with a greater slit separation. Discuss whether you think this change will reduce the uncertainty or not. So the first thing to note, if you've increased that slit separation, that means that you're going to be, instead of dividing 8, you'll be dividing 0.1 by 1 perhaps, or 1.2, a larger number. That means that the percentage error will reduce. So the percentage uncertainty in S1, S2 will decrease. However, we know that for a constant wavelength, we've got our equation lambda equals ax over d. If we increase one of a and x, the other one will decrease. So if we increase, in order to maintain a constant wavelength, because d is constant as well. So if we increase the slit separation, fringe separation on the screen will decrease by a corresponding amount. So increased slit separation will cause a decrease in fringe separation, causing greater uncertainty in the measurement B. However, you've got to remember AB is divided by 5, because remember we're counting 5 fringes. So overall uncertainty will be reduced, and effect on wavelength is reduced as well. Although it causes an increase in the uncertainty in the measurement of AB, ultimately that will have less of an impact on the final answer than the uncertainty in S1, S2. And the reason for that is because you're dividing that by 5. So not wavelength, sorry, dividing that length AB by 5. And on to the final question, question 6. We have a photoelectric cell. There's a cross section through it here. This isn't something you would be aware of, so this is why they've given you all the information you need. The metal plate is coated with potassium in an evacuated transparent tube. A photon of high enough energy instant on the plate to be released from the surface, and it will go towards the collector rod in the middle. Potassium's got a work function of 3.5 times 10 to the minus 19 joules. Show that the longest wavelength of light the photocell can detect is about 570 nanometers. So I would look at this question and go, right, I've got a wavelength. I've got an energy. Well, we've got the equation E equals hc divided by lambda, which we can rearrange to get lambda is hc divided by E. H is the Planck constant, 6.63 times 10 to the minus 34. C is the speed of light, 3 times 10 to the 8. And energy, 3.5. The work function, 3.5 times 10 to the minus 19 joules. This will give us our threshold wavelength of 5.68 times 10 to the minus 7 meters, which is 568 nanometers, so very close to the 570 that we are demonstrating. Remember, this is as it's a show that question, it's even more important than normal that you show all of your working. Part B, there's a potential difference of 12 volts between plate A and rod B, so that the released electrons are accelerated towards and collected by rod B. B is 5 millimeters from A. The light of wavelength 570 nanometers is incident on plate A. Calculate the speed V of electrons arriving at rod B. Okay, so we've got a voltage, and we've got a wavelength. Well, we know that wavelength is the same as the photons above, so that corresponds to those photons. And we've got a distance there. So calculate the speed V of electrons arriving at rod B. In any question like this, you have electrons that are being accelerated by a potential difference. That's giving them kinetic energy. So what we can say is that the energy gained by the electrons, so that can be calculated by multiplying E. So the charge on an electron multiplied is going to be equal to the kinetic energy gained by those electrons, which is half mv squared. We can rearrange that to get V is equal to the square root of 2 times EV divided by M. So that's going to be 2 times 10 to the minus 19 from your formula sheet. That is the charge on an electron multiplied by 12 volts. Divide that by the mass of an electron. Again, this is on your formula sheet, on your data sheet, 9.1 times 10 to the minus 31. And that gives us 2.05 times 10 to the power of 6 meters per second. And we're very nearly there. Estimate the response time of the photocell. That is the time it takes for electrons to travel from A to B. There's 2 marks available here. And I suppose one of the marks is for being slightly smart about what's going on. It is a simple speed, distance, time calculation, or certainly you could consider it that. Alternatively, you could do a SUVAT on this. The easiest way, or the way I approached it, is to look at the electrons journey. Do a quick sketch here, a quick velocity time graph for the electron. It starts with 0 velocity and accelerates uniformly, so you get a triangle like that. The average velocity is going to be equal to half the final velocity. So if the final velocity was 2.05 times 10 to the 6, half of that, 1.025, will give you the average velocity. As I say, you could potentially use SUVAT here as well. I think that would work as well. So the V is going to be equal to the final velocity, 2.05, 10 to the 6, divide that by 2, and gives us 1.025 times 10 to the 6. So speed equals distance over time. We're trying to find the time, so that's going to be our distance s, which we know to be 5 millimeters, divided by the velocity we've just worked out. 5 times 10 to the minus 3 divided by 1.025 times 10 to the 6, and that gives you a final answer, very small number, but that's supposed to be expected, of 4.88 times 10 to the minus 9 seconds. And on to the final part of the question. This photocell is connected to a 12-volt supply and a sensitive ammeter which can detect a current of 1 times 10 to the minus 9 amps. Only 5% of the photons of average energy, 4 times 10 to the minus 19 joules, that hit the plate are released. So what's the minimum light energy that must have been absorbed per second? Quite a tricky question. Actually, in reality, it's sort of just working with the numbers you've got here to eventually work backwards. So it requires an awareness of what each of these quantities represent. And about per second, I will just say, I just like to write at the top of my answer in 1 second, and then from then on, we're dealing with just whatever's happening in that second. So let's work backwards from our ammeter, which can detect a current of 1 times 10 to the minus 9 amperes. An amp is a coulomb per second, so in 1 second, we need 1.0 times 10 to the minus coulombs to be released. That's what we require. So we need to work out how many electrons that represents. So we can do 1.0 times 10 to the minus 9 divided by 1.6 times 10 to the minus 19. That's the charge of 1 electron. And that gives us 6.25 times 10 to the 9 electrons. So in order for our ammeter to detect a current, you would need at least 6.25 times 10 to the power of 9 electrons to be released each second. Worth noting here, I did the number of coulombs required divided by the charge on 1 electron. If you're not sure whether to divide or multiply which around, try it a couple of ways and then look at which number comes out sensible. You're expecting a huge number of electrons. Electrons are very small. This is given as a sensible answer. So always sanity check your answers like that. Now, we know that only 5% of the photons actually produce any electrons at all. So we need to divide 6.25 times 10 to the 9 by 5% by 0.05 to give us an even larger number. Again, that seems sensible. If not all of them are releasing electrons, you're going to need a bigger number of photons. It's 20 times bigger, which is 1.25 times 10 to the power of 11 photons released every second. And we're very nearly there. We know that each photon has an energy of 4 times 10 to the minus 19. So the energy required per second is going to be the number of photons, 1.25 times 10 to the 11, multiplied by the energy of each photon, that's 4 times 10 to the minus 19. And that gives us an answer of 5 times 10 to the minus 8 joules. And that is the end of this question paper, which in my opinion is a very, very difficult question paper. So congratulations to anyone who followed all of that. I will hang around for a few minutes and take any questions. So if you want to ask any questions in the chat box, go ahead. In terms of timing there, actually, the paper is an hour and a half long. I'm not sure exactly what time I started. It was about 10 past 7, so we've actually used less than an hour and a half. Kushal's asking, can you just explain the one before this again? Which question was that? Luca wants to talk about the T on that ball being too big. And what do I think the grade boundaries will be? Well, first of all, deal with that. I have no idea. It depends on how difficult the real paper is. The answer I always say about grade boundaries is you'll get a grade that's fair, and a student that would get an A grade in the old spec or get an A grade in any other would get an A in this paper as well. The grade boundaries will match the difficulty of the paper and the quality of the students that take it. Yeah, sorry, I'll deal with Kushal's first. Part BII, if I just scroll back. Oh yeah, so I have to tell you what, let's try it the alternative way using Suvat. I haven't tested this out, so I'm just sort of doing this live, if you will. The important thing about that question is that the velocity of the electron, it starts at 0 and it's accelerated by being passed through that potential difference. So let's write out Suvat. S is our distance, which is 5 times 10 to the minus 3. U is 0, it's the initial velocity. V is our final velocity, which we know to be 2.05 times 10 to the 6. A we don't know, and to be sorry, T is what we're trying to find out. So we SU, V, and T. So we want an equation that doesn't have A in it. So that would be S equals half U plus V times T. Am I right there? And what you'll see actually is that the effect of this is the same. You end up with, well, let's put the numbers in. So half 0 plus 2.05 times 10 to the minus 9 times T is equal to S. You'd rearrange that and you're going to come out with the same answer. You can try it yourselves, but that would also come out with the same answer. So maybe actually I should have begun with the Suvat approach. That's probably a more straightforward way of doing it. And Luca wants that why was T too big on that ball experiment? That's a really good question. It's a tricky question. It's not the only one. So if we look at the graph, we can see that all of the value, we want all of these values to shift either upwards or to the left. Either of those two changes, in the points being on where we think the line of best fit should be. So let's say there's a problem with the time, that's on the x-axis. We want all of those values to move to the left. That means that T, or in this case T squared, is too large. If T squared is too large, then T must also be too large. So that's why we've deduced that T is too large. You could also say that S is too small. and therefore it should be bigger, and that would involve moving the graph up. So either one could be an explanation for what's gone wrong. Good question from James. What do you think is the best way to revise for the depth paper? I think much the same as you would for any other for the breadth paper as well, is to just practice as many past paper questions as you can find from the old spec as well. Most of the questions will be similar. The only difference in how I'd prepare is I'd be much more focused on the PAGs, the practical assessment, practical assessments you've done during the year. In the spec, there is a list of all of the practicals that you need to be aware of. Take a look through all of those. Make sure you're familiar with them. It's unlikely you'd be asked, I think, to absolutely from scratch say how an experiment works, but well, they could. But the way I would approach any kind of practical question actually is to think about, right, what measurements do I need to take? What equipment am I going to use to take those measurements? And what calculations am I going to do with those measurements? The kind of fourth thing I'd add to that to suit the new spec is what the uncertainty of those measurements would be. So what are the measurements? What equipment will you use? What uncertainty is in that equipment? And what are you going to calculate from that? I think that's a good way. If you can look at every one of the practicals that are required and think about those four things, that would set you off in a good way for that part of the paper. For the rest of the paper, just practice, practice, practice. Yeah, I have to to answer the master. Also, Kushal, regarding the PAGs, it could be any of them. I can't quite remember what was in the first paper you did. I dare say practicals that came up in that paper, for example, does it want to do with the Archimedes principle? I would not expect a long question on the Archimedes principle just because they've already done that in the first paper. The best place to revise for PAGs. My channel's got a few videos going through some of the PAGs, but not many of them. To answer the master in terms of what I would expect to appear, I don't normally like to make predictions. However, we're in a slightly stronger position in a sense this year because you can be examined on all of the content from the course in both papers, which means something that's come up in the first paper is perhaps less likely to go up in the second paper. Kushal pointed it out as well in your first exam, there was a question on internal resistance, so perhaps that's something that won't come up as well. Other new things, Vishali asks in the spec. So the Archimedes principle came up. What else is new? Diffraction. Sorry, not diffraction, refraction of light. So light passing through a glass block and being refracted and so on. That's new, although I think about that in your paper. All these papers seem to be merging together into one in my head, but the specimen, the practice, and the actual real thing. But that's certainly new to your spec. What else is new? The Newton's laws and collisions, although you did have a question about that as well. That's new to the spec. Okay, we've got any more questions? I'll stick around for another few minutes. Yeah, practice, practice, practice. I mean, past papers but not just OCR ones either. In fact, I would say especially take a look at Excel past papers. Especially take a look at the Edexcel past papers. There were for their old spec, there were some papers called the International Option paper or something. I think it was paper 3A off the top of my head, and those papers have practical skills questions. My students, I've already given you quite a few of those questions, but only the multiple choice ones. There are longer questions out there in those papers, very similar to the style of the questions that I would expect in the depth paper. So definitely seek out the international alternative papers for Edexcel, because those ones seem a very good option. Also, if you can get your hands on IGCSE papers, they seem to be pretty good, but they're pretty hard to get hold of. And what was the other thing I was going to say? Yeah, practicing just general old spec papers as well. Questions? Yes, if you look at this paper we've just gone through, some of the questions, not many, but some of the questions were, so it began with simple definition questions. So those would be good to start with. That's a good question, Vishali, about practical skills and safety. Anything to do with risk assessments or anything? But it possibly, yeah, I don't know. Have a look at the spec, see if there's any mention to that. I couldn't tell you, to be honest. Sorry, the master, I couldn't be any more specific. I've got no idea, but yeah, just try out the some of the more specific questions. I'm just looking at some of the recommended. Junkpin's just asked about any other good physics YouTubers. I'm not sure already. I'm just looking at my recommended videos at the side of this live stream. There are some A-level physics online looks to have. They've gone through the specimen paper, which I've done as well, so you can compare those, I suppose. But there's a video called Breadth versus Depth. What's the difference? I've not watched it, but by all means, have a watch of that and see what it does. I've just pasted it into the box for you. Yeah, Dr. Physics A I've come across too. Former colleague of mine, Mr. Godfrey. He's if you just type in Mr. Godfrey, you'll find him. He's got a few videos. Questions. Thanks all for watching. It's been a pleasure. Please feel free to continue discussing it in the comments box. Good luck. I think it was the exam on Thursday. Good luck with that. Good luck with the revision. As I say, practice, past papers. Seek out these Edexcel past papers. Make sure you're familiar with the PAGs. And when you look at it, each PAG, think about what measurements you're going to take, what equipment you're going to use, what the uncertainty is, and what you're going to calculate. Okay. Thank you very much.